Welcome to the Data Science Institute's virtual seminar series. My name is Dr. Sarah Mackey from Lawrence Livermore National Laboratory. Here at Lawrence Livermore, data science has become an essential discipline in many of our key program areas. LLNL is home to many challenging datasets, as well as home to some of the world's most advanced supercomputers. Our data science staff work in a variety of areas, including machine learning, artificial intelligence, big data analytics, statistical inference, predictive modeling, and uncertainty quantification. The Data Science Institute acts as a central hub for our lab's data science activities. We host events like this seminar series in order to introduce new ideas and potential collaborations to our laboratory staff. We invite speakers from outside the laboratory, from the Bay Area and beyond, to share their innovative approaches with our data science community. We're pleased now to include a wider audience in our seminar series through these recordings. You can read about past speakers at our website at data-science.llnl.gov, or you can email us at datascience@llnl.gov. Thank you and enjoy the seminar series. Today we have Matthew Kay joining us. Matthew is an assistant professor who holds appointments both in computer science and communication studies at Northwestern University. He works in human-computer interaction and information visualization. In particular, Matthew focuses on uncertainty visualization, personal health informatics, and the design of human-centered tools for data analysis. His current research is funded by multiple NSF awards, and he has received many Best Paper awards from ACM's CHI and also IEEE Viz. Additionally, he co-directs the Midwestern Uncertainty Collective, and he is also the author of Tidy Bayes and ggDist, which are R packages for visualizing Bayesian model output and uncertainty. Matthew, we thank you for joining us today, and go ahead and start when you're ready.
Thanks very much. Yeah, it's great to be here, and thanks for inviting me. So in this talk, I'm going to give a sort of biased tour of the uncertainty visualization zoo as I see it, and talk a little bit also about some of my research and some work that I've done in studying how people interpret uncertainty visualizations and make decisions from them. So to start it off, I kind of like to ask this question of what happens when we ignore uncertainty. These are probabilistic predictions from 3 poll aggregators of Trump's chance of winning the 2016 US presidential election. So 538 gave him a 28% chance, New York Times a 15% chance, and Huffington Post a 2% chance from their sort of statistical models that aggregate polling information and sometimes other things like economic indicators and such. So obviously Trump did win that election. And the interesting thing about that is, 5 or however many years later, people still think, for example, that 538's prediction was a bad prediction. Of course, from a single probabilistic prediction, you can't really make a good assessment of the quality of that prediction. You might do something like look at the calibration of the forecaster, how often when 538 says there's a third of a chance of something happening, does it happen? 538 actually publishes their calibration information, and they're not too bad on US presidential elections, although of course there's not that many to test against. I should say they're not too bad on election polling in general. But I think the problem here is not necessarily the quality of the prediction so much as its presentation. So here's an alternative way of presenting the same information. This is something called a risk communication theater. So say for 538, you've got 1,000 seats in a theater. The story is I give you a ticket to a random seat in this theater. I've colored the seats black in proportion of Trump's chance of winning the election. If you end up in a black seat, Trump wins. If you end up in a white seat, Clinton wins. I think now, I hope you'd agree with me, it feels a little bit less surprising to learn, say, that you end up in a black seat in this scenario than that Trump wins the election when I just tell you there's a 28% chance. And so the point that I'm trying to make here is that people are very good at ignoring uncertainty, but this is especially true when we provide bad uncertainty representations. Risk communication theaters, for example, are just they're just examples of icon arrays that are used in medical risk communication for things like trying to communicate the different possible outcomes of different treatment options, for example. We call these frequency framing or discrete outcome visualizations of uncertainty because instead of, say, a continuous visual encoding like a bar chart or pie chart to communicate this probability, we're taking 100 or 1,000 items, discrete items, and coloring them in proportion to some possible outcome, for example. So one of the things that I worked on a couple of years ago was the question of how do you do something like this for a continuous distribution? So this is just a discrete distribution with two possible outcomes. What about a continuous distribution? So one example scenario, back when I was doing my PhD in Seattle, there was a system there called One Bus Away. It tracks where all the buses are in Seattle in real time, tries to predict when they're going to show up at the bus stop. So here we have bus number 120, has a 6-minute delay, and is predicted to show up 11 minutes from now. There is a sort of uncertainty representation here. So if I read down on the bottom, it says bus arrival estimates are based on the best available information, but actual times will vary. Well, if my question is, do I have time to get a coffee before the bus shows up? This display is not really doing a lot for me, right? So right now it's essentially telling me something like this. I have a timeline from now off into infinity. Your bus is going to show up exactly 11 minutes from now. But I don't really know, like, if it takes me 5 minutes to get coffee from the coffee shop I'm standing beside, am I actually going to get back in time if the bus makes up that 6-minute delay that it had? A more realistic, or at least more helpful prediction might be something like this, a probability distribution over time to arrive at the bus. If you notice, it is a little bit skewed. It's time arrival data, so it should be. And in general, it's saying, somewhere between about 8 and probably 16 or 17 minutes, the bus is most likely to show up. But there is a long tail there. Maybe the bus gets stuck in traffic. One day when I was still back in Seattle, a fish truck turned over on the highway and shut down essentially the entire city. And that, wouldn't even be visible on this chart in terms of the delays that it caused. But this isn't really the thing that I want either, because if I'm sitting there in the moment, I'm trying to make a decision, the thing that I really want is something like this. If I show up at the bus stop 8 minutes from now, there's a 90% chance that the bus comes after me, which is the same thing as saying that I catch the bus. But this isn't exactly what I want either, because really, depending on the situation, from person to person or from situation to situation, these risk preferences will vary, right? It's a really important meeting, then I need to show up. I want to have like a 99.999% chance of catching that bus. If it's just lunch with friends or I know of other transit options, maybe that goes down to 75%. And so the decision that I make will depend on my risk preferences as well as the uncertainty in that particular moment. And so really what I want is some way of presenting this information to people that allows them to make a decision that aligns with their own preferences at that moment. The other problem here, though, is, so you might say, like, just show them this probability density. Well, there's another problem, which is just a perceptual issue with doing that. So normally in person, I'd do this interactively, but I'll just have you, think to yourself in your head, what do you think the area of the smaller inner circle is as a proportion of the total area of both of these circles? And the vast majority of people, I've run this demo a number of times, will say something like, oh, it's like 80 or 85%. In reality, the smaller circle is 75% of the total area. And the reason why you sort of have that biased estimate here is we have a bias, our estimates of area are biased. As things become larger, we don't perceive them as being as large as they are relative to smaller objects in terms of area. And so you don't see the larger circle as being as large as you should. And since it's the denominator in that ratio, you think the ratio is higher than it actually is. Okay, so maybe not area perception. I said before, I wanted something that was more discrete. So one thing we could do to address the area perception problem is just take the integral, right? Really, in this particular situation, the thing that I care about is these sort of one-sided intervals. So I could use the CDF of this distribution. I could say something like, at 10 minutes, you have a 25% chance the bus comes before you, or a 75% chance it comes after you. Encoding this in position is pretty efficient. We're pretty good and relatively unbiased at reading off positional values, much better than area, for example. But again, I said I wanted something discrete, so I'm going to try something a little bit different. What I'm going to do instead is take evenly spaced values from probability space and project them back into time, and then stack them up into a dot plot. And so we call this a quantile dot plot because it's just a dot plot of quantiles, relatively straightforward naming. But the idea behind this, or the thing that makes this, I think, work well, is that it works in a similar way to the icon array, where you ask to sort of imagine different possible scenarios. And in fact, you can estimate one-sided intervals through counting. So if I show up at the bus, there's 20 dots here. If I show up at the bus stop 8 minutes from now, I miss 2 out of 20 of the hypothetical buses. I catch 18 out of 20 of them, which is, again, is just telling me I have a 90% chance the bus comes after me. The other thing that's interesting about this representation is you can tune it to where in the tail of the distribution you want to be able to make these estimates, because we can do this other thing, which is called subitizing, which is in collections of objects up to about 5 or 6, you can sort of recognize without having to count the amount of elements in that collection, which means if I'm looking at sort of a tail of a distribution and I want to get an estimate somewhere in here or somewhere in here, I can really use subitizing to do that rather than counting directly. And we've run some experiments on this and found that that tends to be the case, right? So as you increase the number of dots in these sort of dot plots, you reach a point where people don't count, or people don't bother to count anymore, and they just use area estimation, and the performance degrades to what you would expect from a density plot. And we have also found in an incentivized decision-making experiment that people make better decisions using things like dot plots compared to, say, densities or intervals in this particular task, which is a really important caveat, because one of the difficulties of uncertainty visualization is you can take the same uncertainty visualization and put it in a different scenario and find that something else will suddenly perform better. And part of the reason for that is that it's sort of this combination of multiple things that determines the performance of the visualization. It's the requirements of the task. So in this case, the fact that one-sided intervals is actually a useful thing to be able to estimate here. It's things like visualization perception, so that problem with area perception here, and uncertainty cognition, the idea of using a frequency framing approach that sort of led to this dot plot approach for this particular scenario. But it won't lead to that same thing in other scenarios necessarily. So what I want to try to do with some of this talk is sort of give some ideas for some of these strategies you can use and some of the sorts of visualizations that I think tend to be potentially helpful. The interesting thing was, 4 years later, 538 actually changed to a representation very similar to this dot plot representation. I've heard through the grapevine that they were inspired by one of the papers we wrote on it. I don't know how true that is. It could be apocryphal, but it was kind of interesting to see. One of the other things that in the 2020 election that I tried to do was push even further on this notion of sort of frequency framing. So I ran a website called Presidential Plinko, where the idea was to take forecasters' predictive distributions for the electoral vote count and try to communicate them in a way that is both frequency framing, but also maybe a little bit more visceral. One of my frequent collaborators, Jessica Hellman, works on these things she calls hypothetical outcome plots, which is basically the idea of using animation to convey uncertainty. And so I was inspired a little bit by that sort of work. And basically the idea here is, to try to find a sort of real world scenario where people are actually familiar with uncertainty, right? And so something like a Plinko board or, a Galton board or a Bean machine, whatever you want to call it, is a sort of physical mechanism that almost embodies randomness in a way that I think people understand a little bit more intuitively. And so the idea was to basically take a predictive distribution and then back out a Plinko board that could generate that distribution, or approximately that distribution, if you dropped a ball from say, the median of the predictive distribution. And this is relatively straightforward. I mean, it's just the height of the board is just related directly to the variance of the distribution on the bottom. And so then I took some of these electoral forecasters, 538 and The Economist, and sort of over the course of the election was displaying these distributions. And then also kind of at the end, I think one of the interesting things you can do is take the actual outcome, which is this, and say, well, okay, how surprised would you be if you had a Plinko board of this shape and dropped a ball from this height, or from this position, I should say, and ended up with this result? And I think that it's an attempt at least to try to make the understanding of the uncertainty here a little bit more visceral and maybe intuitive, although I'm not a big fan of the word intuitive because it's hard to really pin down. So before I talk a little bit more, I do want to do a slight sidebar about what I'm talking about when I'm talking about uncertainty. So for the purposes of the first half of this talk, I'm taking a fairly narrow view of it, and I'm going to try to break this later. But I'm largely adopting a sort of Bayesian view of uncertainty, that uncertainty can be quantified as probability when you quantify it. But I'm going to break this later. It's also useful to talk about, I think, the difference between parameter uncertainty, say uncertainty in a mean or a parameter in a model or something like that, and predictive uncertainty, say a predictive distribution for a single outcome. I'm not going to go too far into these distinctions here, but I think it's useful to kind of have in the back of your head. I think all of these fall generally under uncertainty communication. So how do we think systematically about uncertainty visualization? To me, there's a couple of ways of doing it, and one of them that I found to be useful is to first think about how you derive some distribution describing your uncertainty. So maybe from a frequentist perspective, something like a confidence distribution or a sampling distribution, or from a Bayesian perspective, posterior probability distribution or a posterior predictive distribution or something like that. And then think about ways that you can map properties of that distribution onto visual channels. Where in the visualization sense, when we talk about visual channels, these are essentially just ways of encoding data that that people can read, right? So properties of objects like color, size, position, width, that sort of thing. These are properties that we can map quantitative data onto via some function that hopefully people can then read back. And the reason why I think this is powerful is because you can then reason about the properties of the inferences and estimates that people can make from a visualization. You can reason about their bias and their variance, for example, which can help you understand what a good visualization might be. This also, in some sense, for the purposes of uncertainty visualization research, it abstracts away some of the differences in the sort of small worlds of the way that people do statistical modeling and inference, and allows us to reason more at the level of sort of visual perception and decision making. So I'm going to give you some examples of ways that you can use this sort of approach to construct and maybe reason a little bit about some uncertainty visualizations. So this is from back in 2019, just a time series of unemployment data from the Bureau of Labor Statistics with a very simple and slightly silly structural time series model fit to it to try to make some, frankly, bad predictions about what unemployment might be. Of course, the pandemic happened, so, you know. Right now, we're just looking at the raw data with a density for the posterior distribution for what the unemployment was in April of 2019. If we think about, say, a prediction for what the unemployment would have been in May of 2019, which was not included in this model, so this was a prediction at the time, there's a lot of different ways you can imagine mapping properties of a distribution, and this is not even scratching the surface, onto different visual properties that would convey the uncertainty in some way. So you might build, say, a density plot where you map the density function onto the y position, or you might map the density function onto thickness. And in fact, position against an aligned baseline, like the y position, is more accurate for people to read than the width of something. And so there is actually a difference in these encodings that has an impact on perception. Similarly, if you map density onto something like opacity or really lightness, we aren't as good at reading fine differences in lightness as we are at position. So we should expect that, performance might be different here. On the other hand, depending on your scenario, maybe the precise reading of density values is not relevant. And maybe you're really just trying to get some sense of the overall variance, or even just to give a sort of qualitative sense that there is uncertainty here. And so there you might be thinking more in a metaphorical vein, depending on your audience, maybe if it's more of a lay audience, and maybe a gradient plot might be more appropriate than a density plot, which would arguably be more accurate. Or similarly, you might take like the CDF or the complementary CDF and map it onto position. And I'm going to show a sort of weird version of what that could look like in a second. But here, for example, is the use of density plots on that same chart. Now we're showing uncertainty in the estimates of what unemployment was according to the model, and then uncertainty, predictive uncertainty for what it will be as density plots. But you'll also notice that we lose horizontal resolution in doing this. This is now at a 6-month interval instead of a 1-month interval, because to get the density plots in there, it's kind of hard to also have the 1-month resolution. And so you're really starting to think about like trade-offs in resolution of time versus resolution of uncertainty. And that's, I find, one of the biggest things that happens with uncertainty visualization is you usually have to trade off against some other variable that you're trying to communicate in the visualization. A different approach to the same problem would be to use gradient plot. Now you get more time resolution, but again, your ability to read the uncertainty is going to be much worse here. But maybe that doesn't matter, right? Like, honestly, these estimates from the data that's already happened, the uncertainty here isn't that large, so maybe we don't care. Maybe we care more about the predictive uncertainty. Maybe you use a gradient plot for the previous data and something else for the prediction, right? It's like thinking about these trade-offs in terms of sort of perceptual accuracy and also desired resolution of other variables. Here's a much weirder approach, something we call a complementary CDF bar chart. So the idea is, okay, maybe people are used to a bar chart. Here, if we encode the CDF as a sort of weirdly stretched out bar, where the bar kind of gets pulled in proportion to its uncertainty, you can actually make sort of tail estimates quite easily, right? Like if I go over here in this bar somewhere around 95%, like this is saying I've got about a 95% chance that at least a 95% chance that the unemployment is going to be less than 5%, according to the prediction in November of 2019. And so maybe if that's my task, that's something that I might want to try to play with in this scenario. And so really the idea is it's important to consider tasks and audience and other trade-offs of resolution and accuracy in trying to build uncertainty visualizations. So I'm going to give you a couple more quick examples here. So one of the things that comes up a lot, the infamous hurricane error cone. So this has been studied a lot actually by a group at Utah. We've done some really good work on these things. One of the problems that you run into with a hurricane error cone is exemplary of one of the many problems in uncertainty, of one of the most common problems in uncertainty visualization, which is something called a deterministic construal error. And the idea here is if you put this error cone in front of a lay audience, so this is giving me a 95% predictive interval for where the center of the hurricane is expected to be. you will get maybe about a third of people misinterpreting this as a prediction for what the size of the hurricane will be, which is not on its face an unreasonable misinterpretation because it's area and it's on a map. And most of the time we see sizes of things on maps, they correspond to size in the real world. But it is, of course, also an incorrect interpretation of this visualization. One alternative is to use, say, a spaghetti plot where you have like an ensemble you have like an ensemble and you just show a bunch of draws from this distribution of predicted hurricane paths. And now it's also nice because I can actually see things like the correlation here in this distribution. Like if the hurricane starts going this way, it's not likely to then also go this way. It's much more likely to also continue in this direction, which is something that's totally obscured by the interval. And in fact, that's one of the main values of spaghetti plots, for example. So here's just some simulated data with high correlation at each time step. And here's the simulated data where I've decorrelated each time step from the subsequent time step. If I look at just the marginal distributions and just show you these bands, you can't see the correlation at all. And if I get rid of the spaghetti plots, they look identical. And this is really problematic because sometimes you actually do care about where the path is going and not just conditional on time step or x value or whatever what the prediction is. This came up a lot during the COVID, especially the early COVID prediction models, where people were showing bands like this, and the problem was the correlation in the underlying models was such that you'd see a band that sort of goes up and then goes down. The top of the band, though, a lot of the predictions were actually hitting the top of the band, even though the median wasn't. They were just hitting it at different times. So if you were to predict something like the peak number of cases, it was actually much higher than what the median curve would look like. And so it gave a sort of overly optimistic view of what the peak of the pandemic would look like. Okay. I'm going to take a really brief detour into cartographic uncertainty and try to make this part quick. Cartographic uncertainty is really hard. You often get things like these bivariate maps. I'm not a big fan of these, mostly because you're asked to integrate information from these two different channels when the way that you need to integrate them in order to make some decision under uncertainty is just it's just not it's not very effective, right? If I want to understand the likelihood of some outcome in one of these squares, I need to sort of back out the variance based on this margin of error and then imagine what this distribution might be, and it's just not very helpful. But I'm not a MapViz person, so I'm going to take a brief detour into scatterplot matrices of correlation. So this is just a scatterplot matrix. Each cell there's 8 variables in this data set. Each cell is showing me a scatterplot of one variable against another. Some of them have high positive correlation, some high negative correlation, and some no correlation. A classic version of this without uncertainty, you might show a heat map like this. So red is negative, high negative correlation, blue is high positive correlation. But I want to try to add uncertainty to this. So I'm going to zoom in on the top 3 and just play around with these for a second, and then we'll back it out. So here's a really simple version where I fit a multivariate model and I get correlation values for each of these cells. And so these are posterior distributions for correlation in each cell. This is kind of a crappy version because I'm not relying on any metaphor. High positive correlation could be up, high negative or negative correlation could be down. It'd be a little bit easier to understand. So I could flip these, right? I've also added color back in here. So now every slice of this density I'm coloring according to that red-blue divergent color scale from before. What this means is if I zoom out, I can do something called a micro-macro reading, which is At the macro level, I can kind of stand back and squint, and I can still find these high negative, high positive correlation cells, but I can also sort of lean in and look at a particular cell and see, the distribution for that cell itself. And really, we're sort of trying to rely on things we can do perceptually, like averages over areas of color, to try to build a visualization that gives both a high and low level understanding of this. But I also kind of want to play with something quote unquote more intuitive that I'm not sure is really more intuitive, but we'll go there for a moment. And for each of these cells, instead, I'm just going to take a draw from this distribution in the cell for every pixel in the cell and just color that pixel according to the draw from the distribution. And this is trying to push more in that frequency framing direction again. And I don't really have any idea if something like this would work, but it was sort of like an interesting thought experiment for trying to push a frequency framing approach into this kind of scenario. And really what we're relying on here is kind of the old school idea of dithering, back when we had image formats that only had like 8 bits. So here we have 256 colors and we want to try to make a nice photograph. So what we do is we use this limited palette and we put actually some quite weird colors next to each other that your eye will average out into something more reasonable from far away. And so that same thing called ensemble processing, we can see average colors of cells. We can also see sort of how grainy they are, which is a way of communicating the uncertainty in that cell. You can do this on maps. So here's an example on a map. I can find cells that have similar average value, but more uncertainty. So this one has more uncertainty than that one, which makes sense because this is poverty data and that's a county that has a big city in it. So this probably has a higher sample and therefore probably has lower error. On the other hand, so I was talking about deterministic construal errors a while ago. If you put a map in front of people with a bunch of locations that are colored in different ways, a reasonable misinterpretation of this map might be that the dithering is not communicating uncertainty. It's communicating a very impossibly fine-grained measure of the poverty rate. And so one of the reasons why I bring this example up is it's a uncertainty encoding that maybe in the correlation heat map approach scenario might be reasonable. You put it on a map, I would argue it might be a lot less reasonable because the domain has introduced a deterministic construal error. And so it's really important when you're doing uncertainty visualization to think about these sorts of things in order to try to figure out what's actually going to work in a given context. Which is to say that it's hard. Building effective, complex, correct uncertainty visualizations is hard. Your domain will come and bite you. Prototyping can take time and can be brittle. We really need to be able to navigate the design space effectively in order to try a bunch of different things and then maybe evaluate them and figure out what works. So I've been spending a lot of time trying to solve this problem lately. So one of them is building R packages for actually constructing uncertainty visualizations, as was alluded to in the introduction. I'm not going to go into the details of these, but if you happen to be an R user, you can check them out if you want. TidyBase and ggdist have the links there. And they're really designed for flexible uncertainty visualization. Also, from a research perspective, one of my PhD students, Xiaoying, has been trying to sort of formalize the notion of uncertainty visualizations, at least probabilistic ones, within the grammar of graphics, which is an existing formalism of visualization more generally. I'm not going to go into a lot of the detail of this, but the general idea is that this thing on the left is a grammar of graphics specification for a stack density plot that happens to give you an incorrect stack density plot because the grammar of graphics doesn't know anything about, or at least ggplot doesn't know anything about normalization. So these three areas have equal area when they shouldn't. Basically, what we're doing is the high level bit on this slide is this thing down in the right hand corner, which is we're introducing conditional probability notation into the grammar of graphics, and then we can figure out how to actually respect those conditional probabilities in the visualization to generate the correct, in this case, stack density plot compared to the one on the left, which is incorrect. You can generate a lot of different types of visualizations this way, and we're trying to expand it even more to also include animation. And what I think would be really cool is being able to do this directly from probabilistic programming languages. So things like JAGS or STAN or these other probabilistic programming languages that already use this kind of notation, being able to directly visualize data and samples from those sorts of models, I think would be really powerful. Okay. But the thing, especially for this audience, that I wanted to make sure that I fit in was the trying to step back a little bit from strictly probabilistic uncertainty, because I think a lot of you probably deal with this issue that I'm about to talk about. In data analysis, or at least in some circles, you have this sort of parody of what a data analysis looks like, which is data comes in and analysis happens, and a p-value or a decision or an estimate or whatever comes out the other side. Of course, the reality here is much more complex. There are many different choices for different things you could do during the data analysis pipeline that might lead to an entire sort of combinatorial set of reasonable possible analyses to a data set with their concordant possible outputs. Of course, so this is something called, it comes under a lot of names. Some people call this ontological uncertainty. I like to think of it as a type of specification uncertainty. This is importantly not really quantifiable. If these are, at face reasonable alternative decisions to analyze a data set, you can't really say that a priori they're equally probable. And so you really need to think about this as a way of sort of qualitative uncertainty in a specification or in a result. And so this is where, as a third type of uncertainty, thinking beyond quantified parameter uncertainty and predictive uncertainty, some notion of specification uncertainty. How well does everything that we're doing in terms of the data analysis and modeling actually describe reality? Of course, most of the time we just ignore this, at least in a lot of scientific fields anyway, unfortunately. There are ways of trying to address this, I think, or at least measure it. I think that like having a holdout set or doing pre-registration. The problem with this, of course, is that anytime no good data analysis plan actually survives the data, you actually do have reasonable different ways you can imagine a analysis or a model unfolding, and you don't want to throw that uncertainty away. You really want to try to capture that full sort of combinatorial explosion in some way to describe the uncertainty that you have. So this comes under a lot of names like sensitivity analysis or multiverse analysis. It can be really hard to communicate, right? So now we've reduced an entire complex, interesting, nuanced data analysis in these visualizations down to a single cell communicating a p-value in this case, but it could be anything, right? So your statistical report is now reduced to a single data point on a visualization, and you want to try to still learn something useful. One of the things I've been playing with some collaborators at INRIA is this idea of an explorable multiverse analysis report, where you can give a report to someone and allow them to actually directly explore some of the different ways you could have analyzed the data, and see in real time like how the report would update if you made those different decisions. Importantly, the discussion and conclusion section, so I can actually animate over this and show you some sense of the sort of qualitative uncertainty due to different analysis choices. The discussion and conclusion section, you'll notice, is not changing because it should be written to be robust to your different possible analysis choices. This is still not even close to a solved problem, though. So one of my students now is working on a sort of interactive visualization companion to these sorts of reports to try to help people explore them and understand the sensitivity of the report to different choices. Another one of my students is doing a survey of existing visualization techniques that people have used for this type of uncertainty, sensitivity analysis reporting, to try to understand what sort of task these different visualizations actually support well and which they don't support well. The general problem, I think, is that we need better ways to acknowledge this type of uncertainty and actually have a conversation about it, either through the literature or in other sorts of reports. And again, we're doing some work in this space actively now. The very last thing, and I have, I think, 3 minutes left, so this is perfect, to still have 15 minutes for questions, is one of the more recent things I've done in collaboration with Lace Padilla, who's now at UC Merced. She was doing a postdoc at Northwestern. So this work was with me and her and Jessica Hallman, who's also at Northwestern and is a frequent collaborator of mine. We were looking at what happens when you give a decision maker a qualitative, both a probabilistic forecast and a qualitative assessment of the quality of that forecast. This was kind of inspired by things like IPCC standards for describing like qualitatively the uncertainty in climate forecasts. So we have here, for example, a quantile dot plot showing a distribution from, say, some model of a forecasted temperature. This temperature is being used in the scenarios that we're testing by a disaster relief decision maker to decide whether or not they have to take one action or another. They have a budget, and there are different possible costs associated with, say, a false positive versus a false negative decision in this particular scenario. In addition to actually showing this quantitative uncertainty, we're also showing qualitative uncertainty in this like high, medium, low scale, or we're not showing it at all. And then we're looking at the impact on decision quality. So given the incentive structure and the budget we set up, there is essentially a point at which people should, normatively speaking, if this distribution is taken as accurate, switch from one decision to another. So that's this dashed line here. And what we saw, which surprised us very much, and so we also did a follow-up where we varied some aspects of the experiment and saw fairly similar results, was when we communicated low qualitative confidence in the model, people's decisions became more conservative. So the crossover point moving to the right here essentially represents a more conservative decision in the scenario that we're talking about. So there's no normative distance here. Like, we can't say that you should be this much more conservative when you say qualitatively that your confidence is low, but it does make sense from a normative perspective that the decision should be in that direction, which is somewhat heartening, I would say. Also, it's good that when high confidence is communicated in the model, people are around the optimal threshold in terms of where they cross over from one decision to another. But this is really just like our first attempt to try to understand this. So I think that there's some promise here to the idea that people are able to integrate qualitative and quantitative uncertainty into a good decision. But this is one scenario. This is one uncertainty visualization. We really don't have a good sense of sort of the bigger picture of this type of decision making yet, I don't think. And so just to sum up, I think for quantitative uncertainty visualization, and qualitative as well, like thinking about tasks that people have, thinking about perceptual properties of visualizations, thinking about uncertainty cognition, this sort of frequency framing approach, can help improve uncertainty visualization design. At the same time, the issues introduced by specification uncertainty and other sorts of qualitative uncertainty, we don't know a whole lot about. But I think that there's some hope that we can tackle this problem and improve uncertainty communication in both the quantitative and qualitative domains. That's it. Thank you very much.
Thank you, Matthew. That was a really interesting talk. I really enjoyed the multiverse report concept. It sounds like I'm in a sci-fi novel. In fact, I was reading a novel just the other day with multiverses. So that's very cool. If there's any questions for Matthew, you can type those in the chat, or I also welcome you to unmute and just ask your question directly.
Hi, Matthew. This is Dan Merle. I'm a data scientist at Lawrence Livermore. I was curious if you could talk a little bit about some of the experiments that you do, the decision making, the calibrated risk decision experiments that give you some intuition about the extent to which people correctly perceive or don't perceive uncertainty. And in particular, I'm curious how much like heterogeneity in those effects there are across different populations. At the lab, we're usually, issuing guidance or delivering reports like to either to other scientists or maybe to Washington, D.C. types. And I wonder if there's any, like, if those are weird groups or if they were particularly studied groups, or what you have to say about that.
Yeah, that's a great question. So one of the things that we have done in a couple of so I feel like there's like a two-parter to that, right? So the first part is just sort of what do these studies look like? So often it's something where we give people some kind of a scenario, we give them some kind of payoff incentive structure. So take like the bus catching scenario, for example, way back at the beginning of the talk. We would show people uncertainty visualizations. We would have particular payoffs for things like, in this scenario, you get this much if you make it to your meeting on time. You get this much taken off your bonus for every minute that you're at the bus stop. You have because maybe it's boring or it's raining or something like that. And you get this much added to your bonus for every minute that you get to spend at home before going to the bus stop. So the idea is to sort of set up these incentivized scenarios where then the participants' final payout is in proportion to how well they do on these, like how much fake money they get in these scenarios. So that's like the general setup, because then we can use essentially like the expected payoff under the strategies that people choose as a way of measuring decision quality, and we can compare that to say like some normative standard. That's the general setup. In terms of individual differences, there are a lot. So there's two things I'd say about that. Even when I show, let's say this, which is an estimate of the mean of the population here for the crossover point, the variance of this, I don't have the chart right off here, but like as I recall, the variance is kind of much bigger than this, right? So we do have people who, are going to have crossover temperatures up here or down here. We do have people in this study, for example, who have the shape that we want. We have other people who are sort of more flat and are not sort of responding to this high, medium, low confidence thing. So there's definitely variance that we see in terms of responses. And then I think the very last part, which is essentially like, are there some things that might tell us where these variances come from? So in some studies, we've included things like numeracy scales for measuring people's statistical literacy. And we do see small but very consistent associations between doing better on those scales and doing better at these sorts of tasks kind of across the board, whatever visualization type we show people. I don't have a better I think I don't have a more specific answer than that right now. I think it's a really important question. Some of my research that I'm not really talking about today is on visualization literacy, and that's another piece to this puzzle. Just like there are certain visualizations that you show to some people who aren't familiar with them or don't have strong visualization literacy, they're not going to understand them in the first place.
Thanks.
Yeah.
Looks like we have a few questions in the chat, Matthew.
Mhm.
I'll read them out loud so everyone knows them. Let's see. You mentioned encoding uncertainty in location and size, but when working with spatial data, do you think color is a good candidate for encoding uncertainty? Can you quickly comment on the effectiveness of using colors to communicate uncertainty in data?
Let's see if I can find some of my backup slides somewhere in here. Um, right, so there's a couple things to say about color. Well, I thought I had it in here somewhere. Maybe it's close to the end. Did I go back from the end? Nope. Um, so yeah, right. So often you'll get these sort of like bivariate color maps where some property of the uncertainty is encoded like as as one part of the color scale, and then something else is encoded as another part of the color scale. Uh, so to be honest, besides getting just like a high level gist of like, oh, there's a lot of uncertainty or there's not a lot of uncertainty, I'm not a huge fan of the approach. I think that uh, often, so sometimes that can be what you need for some decision making scenario, but um, to me, I think it's often more useful to be able to understand something like, what's the mean, what's the like high end or low end of what is possible, right? Um, and when you use that kind of color encoding, I think it tends it tends to be a more cognitive process. Like you have to look at that, you have to like decode the color and say what does that mean for what the variance would be, and then given whatever the point value is, what does that imply about what the high or low end of that interval might be. Um, and so you're not really doing visualization at that point anymore. You're translating it into an arithmetic task. um, and so you can't like kind of step back and get good high level understanding. I think I could be wrong, but that's kind of my general feeling about it. I think there are other ways. So one of the ways that you can get around that, but while still using color, would be people do like juxtaposition type approaches, right? So say you have a map, and you do like an interval for a map, which is two maps side by side, where the one on the left is colored according to like the lower limit of an interval, and the one on the right is colored according to the upper limit of an interval. Um, that still introduces some problems, but I think can be more useful, and is one way of using color that I think is helpful. Um, yeah, I don't know if that really, if that didn't answer your question, whoever was going to ask that, feel free to like unmute and tell me that.